Welcome to Chapter 3 of the Adquio web interface. On this occasion, we are going to talk about the configuration of Modbus devices. To do this chapter has 3 parts. In the first, we will see how to configure a Modbus module, both RTU and TCP. In the second, we will see how to configure both RTU and TCP devices. And in the third, we will see how to configure its variables. To create a new module, from the main interface of Adquio, we will go to Devices, Modules. To create a new one, we would give the plus, and, if we want to edit an existing one, as is our case, we are going to use this as an example, we will give the pencil to modify stop bits. Normally, this information is provided to us by the device. We expand. We are then going to see first, how to configure a Modbus RTU module, and later, we will see how the rest of the modules are configured. Very good. Well, we simply select that it is Modbus RTU. In the code, we are simply going to give it a unique identifier that tells us where this module is connected. In this case, it would be a Modbus port and it would be RS4852, that is, why we have given it this name. Now, if the hardware selection part comes, then in this case, we must select which of the 4485 ports which this Adquio has, we are going to use for this module. We know, because we have seen it in the previous report, that port number 1 is busy, so in this case we would say that we are going to use port number 2. Speed, data bits, parity and stop bits. Normally, this information is provided to us by the devices that are connected on that bus, and logically, all the devices that are on the same bus must have the same speed and the same communication parameters. The silence interval is measured in milliseconds and is defined by the device on this bus that is the longest silence interval. This means that between communicating, we must wait 8 milliseconds between message and message. If we exceed this, it is possible that some of the devices on this bus will not respond. As we will see, that it is usual we have a button, in which we can see this information in JSON format, and this allows us to copy this information, take it to our computer, and go to another device and paste it without having to cover all of them again. These data, simply modifying what must be different and unique, such as the code. At the bottom, we have a log that tells us when this module was started and stopped, on what date and at what time. It may be interesting, at the time of installation, to do any type of check, depending on how important this is to us. Maybe in the case of a module, it is not so important, but in the case of a device, for example, or a variable, this information may be more important. Then here we can select how many lines of logs are going to be saved for, in this case, this module. We could put from the 16 that it has, which are the minimum, up to 10,000. In this way, we would always have the possibility of coming to consult it, and examine what happened with this module, in the days, or in the previous months. We are going to return without touching anything, although it is a module that is not connected. Let's see now how we create a new Modbus TCP module. As always, we must put a unique code. In this case we are going to put an example Ethernet, and as you are seeing, it is indicating that it is incorrect because spaces are not allowed. Simply, it would ask us for the destination IP, as we are going to give an example, 192.168.0.100 in the port, then, the port indicated by the manufacturer of the device to which we are going to connect. Well, for example, we are going to put any port, 4500. Interval of silence, it is the same as we have just seen in the previous section. Although, in 485 buses, the silence intervals are more typical than it is necessary to put them, because communication is more critical. In an interface like this, which would be an Ethernet, the usual thing is that there are no silence intervals. As in the previous case, we can see the configuration that we have just made in JSON mode. In case we want to copy it, and we would have the Modbus TCP communication ready, it is very simple. Give it a code, give it a destination IP, and give it a connection port. Let's go back, without saving. We go to create a new device, and for this, we press on this plus icon. And as we can see, the first thing he asks us is the type. This is what we saw previously in the modules. We are going to tell it that it is a Modbus RTU type device. We are going to call it. And we are going to give it a name. We could give you a description. We could give you extra data, that would be sets of pairs of values. Well, we could put a serial number. In this way we can store pairs of values associated with this device. The reading interval is normally 5 seconds. And now, that is where the module asks us, logically the module has to be of the type that we have defined here. We only have a Modbus 485. I am not going to save it, because this 485 is in use, and I must not spoil it, it is in operation. What Modbus slave are we on the bus? Well, normally, if we are the master, we could say that we are 1. The address offset is a base address, that is going to be added to all the variables, that we will define later, and that tells us in which position of the memory of the device, that we are going to read is the block of variables that we need. This is usually especially useful in the case, for example, gateways that convert information from several climate machines, for example, and stores the variables of each machine in a memory block, for example, 100 bits apart. Then, when we define the devices, we would put the first 0, the second we would p at 100, the third we would put 200, the fourth we would put 300. In this way, the first variable of the first device would be 1, the first variable of the device number 2 would be 101, because this base address will be added to the addresses of the variables, as I said before. As in the previous cases, the timeout is the waiting time before a communication is considered failed. You know, we sent a reading and we wait this time for the device I'm interrogating to answer. If this time without response is exceeded, we would give an error. The maximum size of the request in a Modbus communication is the maximum block that I can request from memory to a device. This asks us, because there are devices that have a limit as to how many memory locations I can request in a block. In Modbus, there is the characteristic of reading the variables one by one. I can read a block of variables, and after that we save the content. So, here it is indicating to us what is the maximum value that we want to be able to read from those memory blocks of the devices that we are interrogating. Of course, the value that we put here must be the least common multiple of all the Modbus devices that are worth redundancy on this bus. The values of order of bits and order of addresses that have little endian and big endian as possible values are characteristics that must come in the specifications of the device to which we are connecting. Basically, it is the ordering of the bits within the bytes, from highest to lowest, or from lowest to highest. Very good, with this we have seen how to configure a Modbus device. We are going to leave, as always, from here without saving. In the previous cases of modules and devices, we have seen separately the configuration of Modbus TCP and Modbus RTU, because the physical characteristics of these buses are different. Instead, now to see the variables, we are going to see them only once, since the configuration of each of them is exactly the same. Well, then we are going to enter this device that is based on Modbus RTU, and is on port number 2 of this Adquio. And, at the bottom, we see that we have the device variables and the virtual variables. If you remember, we had seen that the virtual variables were variables that we could add to the device, but that they did not come from it. We did not consult them nor did we survey the device itself, but rather they are variables that we added in some way in addition to those that come from the device. These variables can be interesting, then, to make value conversions and save them here, or states, or any example that we can think of. So, let's see how to create a variable. The first thing we need is to indicate a code that is unique within the current device. Well, then, we are going to call it var1, and we are going to call it variable1. Description: we can describe this variable with a text as wide as we want. Extra data: as we saw in previous chapters, we can create pairs of values, which can be useful to save information about this variable. It is more typical in a device, where you can put, for example, the serial number, next revision date, etc., etc., but in a variable, it is not usually used. It supports reading and writing. This will also be given in the specifications of the Modbus variables from where we are copying this configuration. And there are usually two types of variables. Those that support both reading and writing. Those that only support reading. A good example of this would be a temperature sensor, which gives us the temperature, and we can read it, but we can't write to the sensor. Okay. Reading interval, we are simply going to indicate how often we want it to read this variable from the device. The usual is usually 5 seconds. The type, well, you see, what type is this variable? Temperature, energy, it is an analog output, it is a pressure, it is a voltage, etc. In this case, we are going to put, for example, a temperature. And the units, because we are going to put that they are degrees Celsius. The type fields in the protocol, converters and type in Adquio are dependent on each other. It works as follows. If we select here a type of variable in Adquio, it will automatically put it in type in the protocol, but if inside the converter we do some type of operation, in which we convert this variable to another type, it will take the origin here. Let's put here that this is a decimal of 32 bits. As we can see at the moment, there are no converters. It gives me a decimal of 32 bits, but if we add a converter, we tell it that it is a cast. Cast, we remember that it was used to convert types of variables. We are going to tell you that it is an int 32, and that we convert it to a float 32. Float and decimal are the same. So, we see that automatically he has already taken me, on this side, integer 32 because that's what we have here, int 32. So, he knows perfectly that if on the left side we have an int 32 and on the right we have a float 32, as we have just seen, it is the same as decimal 32, you know that on this side, in the device it has to have an integer 32. In the previous chapter, we have published a table, in which we can check the ranges of values, that the data types in Adquio, both in terms of capacity, of large numbers, and decimals and so on. The mappings, we have already seen, if it were a value, for example, such as the state, we could put here each of the possible values that this variable is going to have, and a literal that tells us, in a much easier way, than means that value. We remember that we had put as an example, a state of a machine, in which we put 0 off, 1 on, 2 auto. Minimum value and maximum value, we remember that we also saw it in the previous chapter, and it served to set what minimum value and what maximum value this DVC admits in this variable. In this way, Adquio will check that if we try, through programming, to set a value in this variable that is outside these margins. In this way, we protect the device to ensure that we never attempt to write unsupported values to it. The value correction is used for the cases in which we have an analog input, for example the most typical case, a PT1000 probe, which is a resistive probe, whose resistance varies depending on the temperature. The problem is that the cable that reaches the probe also has a small resistance, therefore the further the probe is the more false this value will be, the higher the temperature will be, but not because of the resistance of the probe, but rather, by the resistance to the cable that communicates it. So, in an installation, what you do is put the probe in its place, wire it to Adquio, and then with a calibrated thermometer next to the probe, say what temperature it should have, and here adjust the one we see. A typical example would be, if the probe is reading 22 degrees and I come here, but it shows 24, then it would put -2. And we also saw this already, it was simply a place where we can put possible values that should not be given, that if they are given, Adquio must consider them as null, or as it could not read. For example, if this variable we know that it has to have a value between 1 and 5, if we have a 0 here, we know that the value could not be read, because that device would never send us a 0 value. If we have a 0 value, it is not could be read. The Modbus memory field, as you can see, has some values: coil, discrete input, holding register, input register. All these values will be given to us in the documentation that we are covering these variable fields. There will be different blocks of registers, and it will tell us in which of these types of memory is each one of those variables that they are documenting us. Later, we will see a practical example of how to configure the variables of a Modbus device, and this will be much clearer. The address, well, the same, will come to us in the documentation. You can put an address, dot, and the bit that we want to read. only if they are Boolean variables. You can also put values in hexadecimal. For example, we could put here, the address 2, the address 0 by 20, address 2.13, 0x, 0f, etc. In any case, these addresses will be given to us in the documentation. The mask is used only for the Modbus holding register and input register memory types. This mask is used to select which bits of that variable we want to read. If we saw the value of this variable in binary, what we would achieve is that, by placing it on the variable that we have just read, the positions where there are 0 are not used, and the positions where there is 1, if they interest us. We are going to give an example to make it much clearer. If we read the variable, and here, we apply the mask, this what would give us is A, because, as we can see, the positions where we have F are the second and third, then we would take the second and third value. The option to write the complete register is used in cases where the device in which we are writing the variables does not support writing type 22. In this case, a register reading must be performed with function 3, and immediately after write with function 6. This must be indicated by the documentation of the device, if it indicates that the complete record must be written, as we would activate this. As I said at the beginning, only for the cases in which the device does not support function 22, in hexadecimal 0 by 16. Okay, well, with this we have already seen the complete configuration of Modbus variables. We now go with an example. To see a practical example, we are going to use a manual of a real device, which, in this case, is an electrical consumption analyzer. I have extracted here several of the paragraphs that are of interest to us regarding the configuration. It tells us that the Modbus functions that we are going to use are 3 and 4, which are readings of integer registers. Function 5, write a relay. Function 10, writing multiple registers. All of them in hexadecimal. From here, with what we are going to stay is with the first one, simply with the reading of integer registers. We will see why. Okay, so let's go to the first element. First of all, we are going to see the columns it has and what we should look at. Well, logically the first one is the name, phase L voltage. Then, we have the symbol column, which does not interest us in this case. It simply tells us that it is V1, which is the voltage of line 1, but we will not need it. We will then see the instantaneous voltage, which is the one we are going to use, and it tells us that it is the one in position 0 to 1. It means that there are two blocks of 16 bits, the block that is in position 0 and the block that is in position 1. Looking at Adquio, we are going to see that we are only going to keep the first part, with that 00, and we are going to tell it that it is of type integer, because they are 32 bits, that is 2 blocks of 16, and here we see that we have block 0 and block 1. Next, we have the maximum and minimum columns, which in our case, we are not going to use, but which would be other variables that we can also read, and that they would give the maximum tension and the minimum tension, and that it would be in position 106 and position 164. And finally, the last column, we are very interested, because it will indicate the unit of measurement, and if it is multiplied by some value. In this case, as you can see, in the first element that we are dealing with, which is voltage phase L1, it gives us Vx10, it means that this value is a voltage and it will be multiplied by 10. If we change to the configuration of that variable in Adquio, let's review it. Well, we have phase L1 voltage, as is in this case we say that it is voltage from the general analyzer phase L1 voltage, and we indicate that it is in volts. As it is an analyzer, and as we can only read, and also in the specifications indicated it, we are going to put that it is read only. Obviously we cannot write something that is providing us with information. In this case, reading interval every 1 second, we will be questioning this device every second. The type is going to be generic, although we could perfectly put voltage here, and the units, well, we could put volts. We are going to put it. The type of protocol, we know that it is a 32-bit integer. We saw it, because we occupied 2 blocks of 16, 0 and 1. In this case, as we were told that it was multiplied by 10, we are going to make a converter, In the first thing we do is convert the variable type from an integer to a float 64, so that it can support decimals. This is very important, and, in the previous case, where I explained the converters, I did not mention this. If we are going to do a division, and the type of variable in which the data was coming was integer, we must always, first, convert the type of data to one that supports decimals, so that when doing the division it is not truncated. If here we get a 2225, when dividing it we will have a 222.5. If the result, the type of variable in which the result is stored, does not support decimals, we would truncate the 5. So, in this case, since we want to divide by 10, first we convert the variable to one that supports decimals, in this case, a float 64 or decimals 64, and later in the second line, we divide it by 10, because in the documentation, we saw that it indicated that it was multiplied by 10, correct? It is a reading register, it is in position 0, if you remember it, put it from position 0 to position 1, we tell it that it is in position 0. And with this, we finish the configuration of the first variable. Well, the second is current L1, it tells us that it is in position 2 to 3, and that it comes in milliamps. We go to Adquio, we edit, we name it, current L1, as always in these cases, it is read only. We are going to put that it is electric intensity. And we are going to put that it is amperes, correct? The same as before, we know that since it occupies 2 positions or 2 blocks of 16 bits, it is 32, and since it tells us that they are milliamps, what we are going to do is divide it by 1000 to obtain amps. Therefore, we convert the 32-bit integer value back to float of 64, or decimal of 64, and later once we have a variable type with decimals, we divide it by 1000 to get from milliamps to amps. Alright? In this case it is in position 2, as you know in the previous documentation, we saw that it occupied from position 2 to 3, that's it. Let's go with the next one, active power L1, it is in position 4 to 5, and it is in watts, very good, let's go to Adquio. As always, the name, read only. In this case, it is in watts, we are going to select the most correct would be electric power, and we are going to see if we have watts, I suppose yes. Very good, integer of 32, and in this case although the documentation does not put it, it also comes in milliwatts, therefore, we do the same as in the other cases, we convert the data type from integer without decimals to float of 64, which has decimals, and we divide it by 1000. We go with the third value, in this case, it is the active power of line L1, we want to obtain kilowatts and the variable is in the position from 4 to 5. We switch to Adquio, and we enter the active power of line L1. The same as always, read only, integer, and it also has a converter to convert it from watts to kilowatts. The same, conversion of the variable rate and dividing by 1000, okay. From here, they will all be practically the same, we return. We are going to make one now, so that we can see how we convert from hexadecimal to decimal. We are going to take the apparent power L1, which is 0A to 0B. You know that in hexadecimal, when we reach 10 we continue counting up to 15, and it is counted with letters. So it would be 8, 9, A, B, C, D, E, F, okay. So, A would be 10, B would be 11, C would be 12, and so on. Therefore, if we see the apparent power L1 in Adquio, we have it here, we see that it is in position 0A, and that it corresponds to 10 in decimal, okay. We are not going to see the rest of the values anymore, because it is always the same. In many cases, the documentation is not entirely accurate in terms of units of measurement, and we have to do trial and error. We have just seen it, in the case of active power L1, which told us on line 3, that it came in watts, and experience told us that it was not. When we read them, we see that they came in milliwatts, therefore, we had to do the division by 1000. So, in summary, in some specifications of this type, it is important to see, first, what type of readings we are going to have to do. In this case, they are all integer readings, because it tells us at the beginning, functions 3 and 4, reading integer registers. And in this table, what we are going to stay with is the parameter, where it tells us what we are reading in that position, phase voltage L1, current L1, active power L1, etc. And in this case, we were only reading the values, we were only interested in the instantaneous values, then, we were interested in the memory locations. If nothing else is specified, we can extract the size of the variable from that information, that O1 comes to us. In that case, as it indicates that it occupies from position 0 to 1, we know that it will occupy 2 blocks of 16 bits, therefore, we know that an integer value is being stored there, a 32-bit integer value. Obviously, we are also very interested in the last column, where it usually tells you S, if that variable is multiplied by 10, by 1000, etc., although it is not entirely accurate, as we have just seen. Very good. Well, with this we have finished the Modbus device configuration class. See you at the next.